Good morning, children. Continuing with chemical equilibrium, uh, let us consider the topic law of chemical equilibrium. Suppose we have this equilibrium A plus B reversible C plus D. A plus B reversible C plus D. We know that this equilibrium is dynamic in nature. Uh, this equilibrium has forward reaction A plus B arrow C plus D. Forward reaction. So, a rate of forward reaction, the rate at which this reaction is taking place, it will be directly proportional to the molar concentration of reactant A, product of molar concentration of reactant, rate of forward reaction. And from here it follows rate of forward reaction will be equal to Kf A B. This is called rate constant for forward reaction. Suppose the concentration of A is A prime and B prime at the time when we are considering this rate. Okay, now similarly here the backward reaction, is C plus D arrow A plus B. This is a backward reaction, and similarly rate of backward reaction is directly proportional to forward. Backward reaction, the reactant is C and D. The concentration of C, molar concentration of C into molar concentration of D prime. And similarly we have RB equal to KB, molar concentration of C prime, molar concentration of D prime, where Kp is a rate constant for backward reaction. Okay, now we know that at equilibrium we know rate of forward reaction will be equal to rate of backward reaction. That is, at equilibrium Rf is equal to Rb. At equilibrium, now at equilibrium, suppose the molar concentration of A will not be just like this, it will be different. So considering the concentration of A, B, C and D at equilibrium, so Rf will be Kf, molar concentration of A into molar concentration of D, and of B it will be Kb, molar concentration of C, molar concentration of D. So from here we can write this Kf by Kb is equal to C D A B. So now this is a constant, this is a constant. When we divide this, we get a new constant that we write as K, and so K is this. And this constant K is called equilibrium constant. Equilibrium constant. This value is constant for a equilibrium at a particular temperature. This equilibrium constant can also be denoted as Kc. Is also denoted as Kc. Okay, now suppose if we have the chemical equilibrium, say AA, BB, CC, DD. where the coefficients are not same. In that case, law of chemical equilibrium will be what? It will be the coefficients will be raised to the appropriate power. Coefficient will be raised to the appropriate power. So it will be molar constant of C to the power C. For this equilibrium, it will be D to the power D, A to the power A, and B to the power B. For this equilibrium. So so what is equilibrium constant? It is the ratio of molar concentration, product of molar concentration of products raised to appropriate power divided by product of molar concentration of reactants also raised to the appropriate power. So let me take some example to illustrate law of equilibrium. Suppose we have this chemical equilibrium, nitrogen gaseous plus hydrogen gaseous, reversible or in equilibrium with 2NH3 gaseous. So it's to balance it here just with 3. So for this equilibrium, Kc, equilibrium constant, we can directly write the result that we have got here. It will be molar concentration of ammonia raised to the power 2 by molar concentration of nitrogen, molar concentration of hydrogen to the power 3. Let us consider another equilibrium, say PCl5 gaseous, equilibrium with PCl3 gaseous plus Cl2 gaseous. So here Kc will be molar concentration of PCl3, molar concentration of Cl2, molar concentration of PCl5. So this is the value of Kc. Now let us consider one equilibrium where we have a solid component, or where we have a liquid component. So say CaCO3 solid plus CO2 gas. Now molar concentration, if there are some species solid or if there are some species liquid, molar concentration, we should take it 1. We take it 1. I will tell you the reason in the next video. Say for this equilibrium where we have a solid, one solid reactant and one solid product. So here Kc will be molar concentration of CaO, molar concentration of CO2 by molar concentration of CaCO3. And since this is solid, this value will be equal to 1. So ultimately it will be, so Kc will be molar concentration of CO2. So if like this there are some component here in the equilibrium which is liquid, for that also we have to take the value 1. Okay, now children, for gaseous component we have another type of equilibrium constant, that is Kp. That is, if we express the concentration of reactants on products, if we express concentration of reactant and product with pressure or in terms of pressure, then we have this equivalent constant Kp. So what is Kp? Suppose say this equilibrium. Suppose this equilibrium, it is all gaseous. So this we can also express in terms of Kp. So Kp will be what? It will be partial pressure of product, raised to the appropriate power divided by partial pressure of reactant. So partial pressure of N2 and into partial pressure of hydrogen to the power 3. So if we express in terms of molar concentration, then this is Kc. If we express the concentration of reactant and products in terms of their partial pressure, then we have Kp. So next we will try to get what is the relationship between Kp and Kc. This Kp and Kc, what is the relationship, that let us try to find out. So since we know ideal gas equation, that is PV equal to nRT. PV equal to nRT is ideal gas equation. So we write P is equal to N by V RT. Number of moles by volume, this is molar concentration. This is molar concentration, so we can put the molar concentration term RT. So for pressure we can substitute this term. So on substituting this term here for pressure, so it will be molar concentration of ammonia, RT, and this raised to the power 2. Similarly here, partial pressure of nitrogen, so it will be molar concentration of nitrogen, RT, and this one will be molar concentration of hydrogen, RT to the power 3. So from here we will get molar concentration of ammonia square, molar concentration of nitrogen, molar concentration of hydrogen to the power 3, and RT power here it is 2. So 2 minus 1 and here minus 3. Now this quantity is Kc, so we can write Kc, and here RT to the power 2 minus 4, so that is Kc RT to the power minus 2. So for this equilibrium, this relation between Kp and Kc is this. So what is the relation we got? We got Kp is equal to this. And now for general case, I am writing the expression for general case, and I will conclude here today. For general case, suppose we have AA plus BB reversible CC plus DD. So for this equilibrium, your Kp will be equal to Kc RT to the power delta n, we say, where what is delta n here? Delta n will be C plus D minus A plus B. number of moles of product minus number of moles of reactant. So this is the relation you have to remember, relation between Kp and Kc. So this much for now, children. We will be doing lot of numericals in the next video on chemical equilibrium. Till then, goodbye.